Okay, what we've looked at so far in the course is we looked at chemical reactions and balancing chemical equations, and we started to look at this idea that different ratios of chemicals react to produce different ratios of products. And there's an example there of methane burning. Methane is the gas that comes out of our gas taps when we burn our Bunsen burners. And so you've got one particle of methane reacts with two particles of O2 gas or oxygen gas to produce one particle of carbon dioxide and two particles of water. But obviously when we're burning methane, we don't burn one particle at a time, we burn multiple particles at a time. So that's where moles comes in handy, because we've already said that one particle reacts with two particles to produce one particle and two particles, but there's no reason why we can't increase that scale. If we happen to burn 5 particles of methane, that would mean we need 10 particles of oxygen and produce 5 particles of carbon dioxide and 10 particles of water. And we could pretty much burn any number of molecules we want, but these ratios we've got up here always have to stay the same. One molecule of methane always reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 of water. And so that's what it says here. X plus 2x particles goes to X plus 2x particles. And as we know, a mole is just a number. And just like in mathematics, we can replace that X with any number we like. So we can turn this ratio of molecules reacting into what we call the mole ratio. So if we happen to burn 1 mole of methane, like down here, 1 mole of methane, that means we need 2 moles of oxygen, and that will produce 1 mole of carbon dioxide and 1 mole of water. And knowing that, it becomes very handy because we can then start using chemical reactions, not just to figure out how many moles of chemicals react, but we also know how to convert between moles and mass. We can actually start figuring out masses of chemicals reacting with each other. And it's also similar in gas reactions. We've also got another couple of rules for gas reactions. We've got Gay-Lussac's rule, that gases react in a simple whole number ratio to each other by volume. And for example, you've got this reaction here between hydrogen and nitrogen turning into ammonia. And we know that 3 particles or 3 volumes of hydrogen gas will react with 1 particle or 1 volume of nitrogen gas to produce 2 particles or 2 volumes of ammonia gas. And you might be asking why. Why do these things react in simple whole number ratios to each other by volume, not just particles? And it comes in because of Avogadro's law. He showed us that equal volumes of gas contain the same number of molecules. So for gases, that means the mole ratio in front of our components of our equation, these prefixes here, 3, 1 and 2, is also the volume ratio. And that's shown in the diagram down here. We can see over here you've got 3 particles of hydrogen, which is equivalent to 3 volumes based on Avogadro's law, or 3 moles if you want to think about it that way, reacts with 1 particle of nitrogen, or 1 volume, or 1 mole, to produce 2 volumes of ammonia, otherwise known as 2 particles or 2 moles. So with normal reactions that don't all have gas phases, we can just say that it's a particle ratio or a mole ratio. But with gas reactions where all the components are gases, we can also say this ratio here, 3 to 1 to 2, is not just a particle ratio, it's also a mole ratio, and for gases it's also a volume ratio. So let's look at some examples where we use these chemical reactions to figure out problems. You've got example 9 in your booklets, and it says for the following reaction, and it is 3 SiO2, 3 silicon dioxide solids, plus 4 carbon solid, turns into 2 carbon monoxide gas, plus 2 carbon dioxide gas, plus 3 solid silicon. Now all these phases aren't gases, so we can't apply Avogadro and Gay-Lussac's law to the whole equation, but we can apply this concept of the mole ratio. And the first question says, how many moles of each reactant will be required, and how many moles of each product produced if we have 1 mole of silicon dioxide? And the easiest way to solve these problems is to first write down what we call the mole ratio. And we can write down here, because of these exponents out the front, that 3 silicon dioxides react with 4 carbons to produce 2 carbon monoxides, 2 carbon dioxides, and 3 solid silicons. We've got this mole ratio, 3 to 4 to 2 to 2 to 3, or 3 moles of silicon dioxide react with 4 moles of carbon to produce 2 moles of carbon monoxide, 2 of carbon dioxide, and 3 moles of silicon. But we've only got 1 mole of silicon dioxide, and our ratio has 3 moles. So the simplest thing to do in all these equations is for the thing you're given information about, the thing you're told the moles of, you make that equal to 1 in your ratio. So we've got to try and convert this 3 here into a 1 in our ratio. And the simplest way is to divide by 3, but when you divide that by 3, you've got to divide the whole lot by 3. So that means if we divide everything here by 3, that means if we've got 1 mole of silicon dioxide, it'll react with 4/3 or 1 1/3 moles of carbon, it'll produce 2/3 of a mole of carbon dioxide and 2/3 of a mole of carbon monoxide and 1 mole of silicon. So using that mole ratio, we can quickly see how many moles of reactants and products we need to react a certain number of moles of one of our reactants. Second question for part B, it says, well, what if we haven't got 1 mole of silicon dioxide? What if we've got 2.5 moles of carbon? Well, similar to what we did before, now we want to make sure, we want to convert this thing we know. This time it's the carbon we've been told about, so we want to make the carbon the 1 in our ratio first. So what we do first is make carbon 1 in the ratio, so we divide everything by 4 this time. So that means the ratio is now 3/4 as to 1, as to 1/2, as to 1/2, as to 3/4. And it's produced a ratio now where the thing we know about, the carbon is what we've been getting information about, is the 1 in our ratio. And the reason we do that is because now we've got carbon as the 1 in the ratio, it's easy to convert that 1 into 2.5 in our ratio. So now we just times everything by 2.5. So once this has become 1, we can times everything by 2.5, and I'll leave that up to you to figure out the numbers, but this would basically be 2.5 times 3/4. This will be 2.5. 2.5 times 1/2 is 1.25. I can do that in my head. That's nice and easy. That's 1.25 as well, and that'll be 3/4 times 2.5. So the best trick is the thing you've been told about, in this case the silicon dioxide, in this case the carbon, you convert what you've been told to 1 in your ratio first. In this case we divided by 4 to get all these in the ratio of 1 carbons. Then we just times by the thing we need to times by, which in this case is 2.5. And you use a very similar technique for C in example 9. In that case though, you've been told you've got 1 times 10 to the minus 2 moles of carbon monoxide. So the first thing you do is want to convert this ratio to having 1 at the carbon monoxide. So that'll be 3 on 2, as to 2, as to 1, as to 1, as to 3 on 2. All I've done is gone through and divided all these ratios by 2 to make sure the carbon monoxide is now 1 in my ratio. Then I've got to times all these by 1 times 10 to the minus 2. And that's a very easy way to figure out how many moles of reactants and products you have for any given amount of reactant or product.